Hello and welcome to the last section of the textbook, which is going to be about Einstein's theory of relativity, special and general. As an eager young student of physics in the 1890s, Einstein was troubled by a difference between Newton's laws of mechanics and Maxwell's laws of electromagnetism. Newton's laws were independent of the state of motion of an observer. Maxwell's laws were not, or so it seemed. Someone at rest and someone in motion would find that the same laws of mechanics applied to a moving object being studied, but they would find that different laws of electricity and magnetism apply to a moving charge being studied. This is in reference to Newton's first law, which, if you'll remember, stated that there were no privileged reference frames. No matter what speed you were going at, as long as you were going at a constant velocity, then all of the laws of physics should remain the same. However, Maxwell's laws were the laws of electromagnetism, where a charge that was moving would have a magnetic field, while a charge that was not would have an electric field. Therefore, if you had a charge that was moving in one reference frame and not moving in the other, then that would mean that you would have an electric field in one reference frame and a magnetic field in another reference frame, which did not immediately make sense, though it turns out that this does generally end up being the thing. If a magnetic field only occurs if there's a velocity, then that would suggest that there is some reference frame that is more privileged than others, where the magnetic field is occurring in reference to. To test this, Michelson and Morley set up an experiment where they tried to find the difference in speed of light if you were looking in two different directions. And this difference in the speed of light would tell us how fast light was going according to this privileged reference frame. It would tell us how fast the Earth was moving through space in reference to what was called the ether. However, what they found was that if you measured the speed of light in one direction and the speed of light in another direction, it came out to be the same speed. This was very interesting because this means that no matter what velocity you're going at, if you're going forward at the velocity of the Earth or backwards at the velocity of the Earth, you are always going to have the same speed of light. The speed of light is constant no matter what reference frame you're looking at, no matter what inertial reference frame you're looking at. When trying to decipher this, Einstein came up with a couple of postulates that he used to develop his theory of relativity. The first is that there are no privileged reference frames. All laws of nature are the same in all uniformly moving frames of reference. And the second is that the speed of light in free space has the same measured value for all observers, regardless of the motion of the source or the motion of the observer. That is, the speed of light is a constant. An interesting consequence of this that immediately pops out is that two events that are simultaneous in one frame of reference need not be simultaneous in a frame moving relative to the first frame. So, for example, if you have a light bulb that is emitting light from the center of a room, then from your reference frame, the light is going to hit both edges of the room at the same time because it travels the same distance from the center of the room. If, however, you're in a rocket ship that's moving relative to the ground, the observer on the ground will see that the light is going to hit the back of the rocket ship first because the back of the rocket ship is moving towards the light, whereas the light is going to hit the front of the rocket ship later because the front of the rocket ship is moving away from the light. This means that while you see the two events as simultaneous, somebody who's observing from a different reference frame will see the two events as happening at different times. For similar reasons, if you are in a rocket ship and you shine a light bulb up into the air and then reflecting back from a mirror on the top of the ceiling, then it's going to cover a certain amount of distance in that time. However, if somebody is looking at you from the ground again while you speed by, what they will see is that the light has to bounce up and to the side as well as just bouncing up and down because you are moving to the side. This longer diagonal distance must be divided by a correspondingly longer time interval to yield an unvarying value for the speed of light. This stretching out of time is called time dilation. The time that the observer on the ground sees is equal to the time naught, t naught, over the square root of 1 minus the velocity that you're moving at over the speed of light squared, which is equal to gamma times this time interval from your perspective, where gamma is 1 over the square root of 1 minus v over c squared. Combining the ideals of simultaneity not being the same between different reference frames and the ideal that time intervals are not the same between different reference frames, we bring up the ideal of a space-time interval. So in Galilean reference frames, the distance between 2 points or two events is always the same. Delta r squared is constant, where r is the distance between the two events. The quantity in Einsteinian reference frames is called the space-time interval, which says that the space-time interval squared is equal to c times the change in time squared minus the change in distance squared. So as time stretches out, space compresses and vice versa for the same two events. This gives rise to something called length contraction, where L equals L naught times the square root of 1 minus V over C squared, rather than 1 over the square root of 1 minus V over C squared. If you're looking at a baseball going at increasingly fast speeds, then the width of the baseball in the direction that it is moving is going to get smaller and smaller as the length contracts. If you're looking at a meter stick that is a meter long in the reference frame of the very fast meter stick, then the very fast meter stick or a meter stick that's been thrown at half the speed of light is going to contract from your point of view. So the meter stick is actually going to look shorter than a meter. Most people know that if you walk at 1 kilometer per hour along the aisle of a train that moves at 60 kilometers per hour, your speed relative to the ground is 61 kilometers per hour. If you walk in the same direction as the moving train and 59 kilometers per hour if you walk in the opposite direction. What most people know is almost correct. Taking special relativity into account, one's speed are very nearly 61 kilometers per hour and 59 kilometers per hour, respectively. For everyday objects in uniform, non-accelerating motion, we ordinarily combine velocities with the simple rule v equals v1 plus v2. But this rule does not apply to light, which is always the same velocity. Strictly speaking, the above rule is an approximation of the relativistic rule for adding velocities. The rule is v equals v1 plus v2 over 1 plus v1 v2 over c squared, which becomes c if one of the velocities is c, confirming that there are no privileged reference frames. In addition to length and time being different depending on the relativistic reference frame you're looking at, we also find that momentum equals gamma mv and energy is equal to gamma times mc squared, which is equal to the square root of mc squared plus the momentum times c squared. This is another version of mass energy equivalence, E equals mc squared, where m can be considered to become larger as speed goes up. Another ideal that's not treated in the book, but is very important to the beginning of the chapter, is the fact that electric fields and magnetic fields kind of do convert into each other depending on the reference frame. If you look at a reference frame where the charge is stationary, then you will only get an electric field. However, if you look at a reference frame where the charge isn't stationary, you will get a magnetic field. There's a pretty complicated relationship between the electric and magnetic field that is actually a little more complicated than just gamma. However, if you look at low speeds, it goes to our old rules about electric and magnetic fields. Additionally, P becomes mv in the case where velocity is very, very small compared to the speed of light, then in that case it becomes mv. T goes to T naught, L goes to L naught, and E goes to the initial mass times c squared plus 1/2 mv squared, or the mechanical kinetic energy that we get from classical mechanics. This is another example of the correspondence principle.